This PowerPoint is designed to take you through the content from Module 2A in my AP Environmental Science class. Module 2A includes biogeochemical cycles, geology, atmosphere and weather, ozone and climate change, and water resources.
The first major content area in Unit 2A is biogeochemical cycles. These look at the ways in which nutrients, elements, and compounds are moved through biotic and abiotic components in the environment. Of these biogeochemical cycles, you should be able to draw and label from memory the hydrological or water cycle, the carbon and the nitrogen cycle. You should be able to explain and recognize components of both the sulfur and the phosphorus cycle. For sulfur, natural sources are exclusively volcanic eruptions and deep sea ocean vents. Anthropogenic or human sources come largely from burning fossil fuels. For the sulfur cycle, it's important to know SO2 or sulfur dioxide, which is a component of acid rain, and dimethyl sulfide, DMS, which is a requirement for condensation of water in the atmosphere. For phosphorus, you should know that it's exclusively in the lithosphere, hydrosphere, and biosphere. It never enters the atmosphere. Naturally, it occurs in rocks, and it's through erosion in uplifted rocks. Humans produce phosphorus by using soaps and detergents, as well as using synthetic fertilizers such as NPKs. This is the hydrologic cycle. It is important to be able to identify precipitation, evaporation and transpiration, solar heating, surface runoff, infiltration, and groundwater. Infiltration is the process of percolation, or the movement of water through the open spaces in soil, and leaching, which is when that moving water carries nutrients deeper into the soil. It is important to be able to identify, along with the hydrologic cycle, the parts of a river and an aquifer, but we will cover that later. This is your carbon cycle. For the carbon cycle, it is important to know photosynthesis and cellular respiration, as well as the extraction and combustion of fossil fuels. It's also important to know that when living organisms die, they go through the decomposition process that releases carbon. If those dead organisms are placed under appropriate heat and pressure and given enough time, they can become fossil fuels. It's important to also note that atmospheric CO2 can be dissolved into the ocean. When atmospheric CO2 is dissolved into water, it goes through the process of producing an acid. That acid, H2CO3, can break down in the water. That produces H+ and HCO3 negative. The H+ is responsible for contributing to the acidity of ocean water. That ocean water, when it becomes acidic, can damage ecosystems and cause organisms with calcium carbonate shells, such as coral reefs or clams and other organisms like that, to lose their shells because the shells dissolve. It is partly because of the acidic compound of the water, and partly because the dissolved carbon takes the calcium and it keeps organisms from being able to acquire it. This is a sample of your nitrogen cycle. This one is important to be able to explain and draw, as it is impacted and impacts multiple components of your ecosystem and your human activity. It is important to be aware that there are bacteria that occur at each step and that do the chemical processes that these steps are named after. Beginning with atmospheric nitrogen, this goes through the process of nitrogen fixation by nitrogen-fixing bacteria. This is most often cyanobacteria related to plant roots. Nitrogen fixation turns N2 into ammonia, which then goes through this process called ammonification to produce ammonium. Ammonium is the first part of the nitrification process. In nitrification step 1, ammonium is turned into nitrite. The second step of nitrification is to turn nitrite into nitrate. Nitrate is then able to be assimilated by plants. Plants then are eaten by animals, and then both plants and animals decompose. The nitrogen that they release when they decompose goes back into the ammonification process, most often as ammonium. Nitrate can also go through the denitrification process. Denitrification takes NO3 negative, or nitrate, and converts it back into atmospheric nitrogen. It's important to note that humans impact the nitrogen cycle at the nitrate process. By adding synthetic fertilizers, such as NPK, this increases the amount of nitrates and can overload the cycle. Too many nitrates can lead to the process of cultural eutrophication, when nitrogen runs off into bodies of water. This causes bacteria to overgrow, and it causes algae to overgrow. That is the process of eutrophication, but because humans are impacting the process in an accelerated way, we call it cultural eutrophication. Now that we've looked at the three main biogeochemical cycles, let's start talking about geology. The first thing to understand is how rocks are formed in the first place. There are three kinds of rocks that we talk about in the lithosphere, or the crust part of the Earth. And those three types of rocks are igneous, metamorphic, and sedimentary. All three of these types of rock can convert into the other through a various set of processes. Let's start with igneous rock. Igneous rock is formed when magma from the interior portion of the Earth cools and crystallizes. If igneous rock is put under appropriate heat and pressure, it can form into metamorphic rock. Additionally, if igneous rock is subjected to erosion, weathering, transport, and sedimentation, it can turn into sedimentary rock. Igneous rock can also turn back into magma through the process of subduction and melting. Metamorphic rock can melt and become part of the magma that will form igneous rock. It can also be put under weathering, erosion, transport, and sedimentation to form sedimentary rock. Lastly, we have sedimentary rock. It can be weathered, eroded, and compressed to form sedimentary rock. That comes from igneous or metamorphic. Sedimentary rock can also undergo subduction and melting and produce the magma that's used to produce igneous rock. If sedimentary rock is put under heat and pressure, it can also form metamorphic rock. Let's take a look at Earth's structure. When we talk about the structure of the Earth, we are talking about three major components: the core, the mantle, and the crust. The crust is the area where we reside, and it is made up of the lithosphere and the asthenosphere. The lithosphere is the solid piece. The asthenosphere is the top portion of the mantle that has a kind of plastic consistency. It is on that asthenosphere that the plates that make up the crust sit. Beneath the crust, we have the mantle. The mantle makes up the majority mass of the Earth and is liquid melted rock. It moves through the process of convection, where warmer magma will rise and cooler magma will fall. Below the mantle, you have the core, and the core is broken into two pieces: the outer core and the inner core. The outer core is liquid. The inner core, however, is solid, and it is from the inner core that we get the magnetic fields that surround the Earth.
Here, let's talk about the process of plate tectonics. Plate tectonics is the idea that the crust of the Earth is made up of separate giant blocks. These blocks are called plates. The plates sit on the mantle, and remember that the mantle is fluid. The upper portion of the mantle is called the asthenosphere. This is where those plates rest. As convection occurs, warm magma rises to the surface while cooler magma falls down. This process of rising and falling actually causes movement. There are three different ways in which plates can move. We can talk about them in terms of divergent boundaries, convergent boundaries, or transform boundaries, or transform faults. Let's look at each of these in turn. At a divergent boundary, two plates are moving away from each other. While you most often see this between two oceanic plates, sometimes you do see it with continental plates, such as the Great Rift Zone in Africa. At a divergent boundary, two plates move apart from one another. This allows magma from the mantle to rise up. This may create new seafloor, leading to seafloor spreading, or if the process takes place over a much slower time frame, it can cause underwater mountain ranges, such as those found at the Mid-Atlantic Ridge. There are three kinds of convergent boundaries, and they have to do with the kinds of plates that are interacting with one another. Keep in mind that if there is a divergent boundary on one side of a plate, there has to be a convergent boundary on the other side. This is because the circumference of the Earth never changes. The three types of convergent boundaries are continent-continent, continent-ocean, and ocean-ocean. Let's take a look at those in turn. When two continental plates meet, they both have equal mass and density. The plates meet, and they force folding of the crustal plates. This leads to the formation of mountain ranges. The best example of this is when the Indian subcontinent plate rams into the Asian plate, creating the Himalayan mountains. Then you have continent-ocean. This happens when an oceanic plate meets a continental plate, and because the oceanic plate is much more dense, it's going to meet the plate of the continent, and it's actually going to slip underneath. That slip underneath is called subduction. As the plate from the ocean goes into the mantle, it gets warmed, and you have an area of magma that is incredibly hot. That magma, if possible, will find cracks in the continental crust and rise to the surface. This can form volcanic mountain ranges along the coast of a plate. An example of this would be the mountain range on the western part of the United States that includes Mount St. Helens and Mount Rainier. The last is ocean-ocean. When two oceanic plates crash into one another, there are a couple things that could happen. Most commonly, they meet and one of them is forced underneath in subduction. Sometimes, however, they will meet and they will actually both force one another under, and this will form what we call a trench. There is a slight difference between trenches and subduction zones, but as far as the AP exam goes, you don't really have to make that distinction. The last one is the transform fault, or the transform boundary. This is where two plates slip beside each other. This can happen either horizontally or vertically. It's at transform faults that we have earthquakes. In plate tectonics, we understand that the plates are moving. Underneath, you may have areas of magma that become superheated. When a continental plate or an oceanic plate most often moves over one of these so-called hot spots, the magma will rise up through any cracks it can find. As that magma rises up, it's going to eventually form what's called a volcanic mountain. That volcanic mountain will eventually become an island. But the plate is not stationary. As the plate slowly moves over the stationary hotspot, the process repeats itself, and you get what's called a volcanic island arc. You most often see this in areas such as Hawaii or the Aleutian Islands off the coast of Alaska.
Briefly, let's discuss the types of volcanoes that you will see. Most volcanoes fall into one of three categories: a composite, a cinder cone, or a shield volcano. Composite volcanoes are the ones that you're most familiar with. These include Mount Vesuvius and Mount St. Helens, both of which produce large amounts of both magma and gas and ash. These are the most damaging and the most destructive. Cinder cone volcanoes tend to produce very little magma when they erupt. However, they do produce things called lava bombs. These are pockets of lava that are encased in partially crystallized rock. Cinder cones produce more ash than they do anything else. An example of this is Paracutin, which is a volcano that's found in Mexico. Lastly, you have shield volcanoes. These are almost exclusively island volcanoes. In a shield volcano, it is very low and sloping, and while it produces more magma than any of the others, the magma is very slow moving, so it isn't very destructive. We've talked plate tectonics. We've talked volcanoes. Now let's talk about earthquakes. Earthquakes occur at transform faults and can occur when plates move either side to side or up and down in relation to one another. When transform faults occur, those plates are moving past each other and build up friction. That friction sometimes causes them to get caught. When they get caught, pressure builds up until they release, and that release is a rapid movement of the plates, either side to side or up and down in relation to each other. The area exactly where the pressure builds up and is released deep in the crust is called the focus, or the hypocenter. If you go directly on the surface of the Earth above the focus, you will find the epicenter. This is where the waves are first felt on the surface. There are three different types of seismic waves: P waves, S waves, and surface waves. P waves are found first, S waves arrive second, and surface waves are the ones that cause the rolling motions on the surface of the Earth. Remember that earthquakes are measured on a Richter scale. When we talk about magnitude between a 1 and a 2 on the Richter scale, remember that is logarithmic. It's a 10 scale. When we talk about energy release, that is a 32 times scale. So the difference between a 1 and a 2 is 32 times more energy. When earthquakes occur underneath the ocean, they can form what are called tsunamis. The movement of the plates side to side or past one another displaces the water above it. That displacement causes the water to move. As the water moves closer to the shore, the water has less and less space to move in. That causes the waves to get bigger and higher. By the time they reach the shallow sea, those waves are incredibly high and can be incredibly destructive. Now that we've talked about the lithosphere, let's talk about the atmosphere. The atmosphere is the gases that encompass the Earth, and it's made up mostly of nitrogen. However, the atmosphere does include oxygen, carbon dioxide, methane, ozone, and argon in trace amounts. The atmosphere is divided into 5 separate sections: the troposphere, the stratosphere, the mesosphere, thermosphere, and the exosphere. The thermosphere is the largest by mass. However, for us, it is not the most important. We live in the troposphere, and this is where weather occurs. For the troposphere, it is important to know, as you increase in altitude, you decrease in temperature, until you reach what is called the tropopause. This is the area where the troposphere transitions into the stratosphere. At that tropopause, you will find the stratospheric ozone layer. This is a layer of ozone gas, O3, that is important to help protect the Earth from ultraviolet radiation. The sun produces ultraviolet radiation in forms UVA, UVB, and UVC. While the ozone layer can block some of all three of these, it is best at reducing UVC. Ozone forms naturally in our atmosphere, and it decomposes naturally in our atmosphere. This occurs when an oxygen molecule, O2, binds with a free oxygen through the interaction with ultraviolet radiation. O2 and O is catalyzed by the sun to form O3. That O3 can break apart the same way. It interacts with ultraviolet radiation, and a free oxygen will break off, forming O2 and the free O. This is a normal process, and it happens continuously in our atmosphere. There are times of the year where it happens more frequently, and that is based on solar intensity and the direction at which the Earth is tilted. However, there are processes that break ozone down unnaturally. This is most commonly associated with what is called a chlorofluorocarbon, or a CFC. CFCs were used extensively in refrigerants, things that were used in refrigerators and air conditioners, as well as propellants in aerosol cans. Here's what happens. When a CFC molecule enters the atmosphere, it interacts with ultraviolet radiation. That radiation causes a chlorine atom to break off of the CFC. That chlorine atom is highly reactive as it is a free radical. The chlorine will find an ozone, and when it interacts with that, the chlorine will strip off one of the oxygens, leaving O2. The chlorine will then release that oxygen and complete the process again. CFCs are very good at breaking up O3, so much so that they reduce it much faster than the natural process can replace it. CFCs also have a very long lifespan in our atmosphere, around 50 years. So even though the Montreal Protocol of 1989 made it illegal to use it in developed countries, unfortunately developing countries are still using it because it is a resource that is cheap and is easy to manufacture. Now that you understand how the atmosphere works, let's talk about global climate change. When we talk about global climate change, we are talking about changes in patterns of temperature and precipitation over long periods of time. Global climate change is part of a larger problem, and that is called global change. Overall global change includes rising sea levels, increased use of fossil fuels, atmospheric and water contamination, loss of organisms, and increase in diseases. Global climate change, however, is directly looking at increased storm intensity, patterns of precipitation and temperature, changes in ocean circulation, and the process of global warming, where trends tend to indicate that land, air, and water are becoming warmer. This also leads to increased heat waves and less strong or less lengthy cold spells. Now that you understand how the atmosphere works, and we've talked about global climate change, let's talk about one of the biggest anthropogenic factors in global climate change, and that is changes in the greenhouse effect. The greenhouse effect is a natural and required process for making Earth sustainable for life. Greenhouse gases include carbon dioxide, methane, and water vapor. Those molecules are very good at reflecting solar radiation. When infrared radiation leaves the sun and arrives at Earth, some of that infrared radiation is reflected back into space. That reflection comes from those greenhouse gases, cloud cover, and the Earth itself. Areas that are high in ice, such as the polar ice caps, are also very reflective, as they have a high albedo, or reflective index. Solar radiation that makes it through the greenhouse layer is going to hit oceans and land, be absorbed, and re-radiated. Some of it is reflected back by the greenhouse gases, while some of it is able to exit. Humans, however, are adding extensive amounts of greenhouse gases to our atmosphere, specifically in the form of carbon dioxide. A thicker greenhouse layer makes it more difficult for solar radiation that makes it through to be reflected back out into space. This traps that heat and infrared radiation near the surface of the Earth, which causes areas to become warmer. This graph shows you CO2 concentration in years. It's easy to see that from 1954, as our CO2 use has increased, so has our average yearly temperature. This is heavily associated with the use of fossil fuels, as the 1950s was the time when more people were being able to purchase cars and being able to drive them. These graphs are associated with ice mass in Antarctica and Greenland. As you see, from the early 2000s to 2017, the overall average ice mass has decreased. This is because areas are becoming warmer than usual. When solar radiation is absorbed by water, the water heats. As that water heats, it melts sea and land-based ice. As that ice melts, there is less albedo, or less reflectivity of that ice, which causes more solar radiation to be absorbed rather than reflected, increasing the process in a positive feedback loop. In addition to changing the albedo, increased melting and loss of ice mass contributes to a rise in sea level. As the ice melts, that ice melt is released into the ocean. It causes areas to experience higher sea levels, stronger tides, and it can impact ocean currents that transfer heat from parts of the Earth to the poles. When those ocean currents are interfered with, it can drastically change the stable climate found in an area. So why should we worry about climate change? There are multiple global effects. These include extreme temperatures, increased drought, which will lead to lower agricultural yields and increased famine, hunger, and disease. The migration of diseases to areas that they weren't originally found. This means that they tend to move further north or south, and vectors, or things that carry diseases, travel with migrating animals. We also have melting land-based ice, which increases the sea level and the dilution of normal ocean temperature and salinity. Thermal expansions of the ocean, where they absorb heat, and when things become hotter, the molecules separate from each other, expanding them, making them bigger. This can impact sea levels. You also have coral bleaching, where changes in pH and temperature of ocean water causes corals to lose the symbiotic organisms that live on them. They lose their color and eventually will die. You also have ocean acidification, those rising sea levels associated with loss of coastal ecosystems, saltwater intrusion to groundwater, and loss of property. Diminishing freshwater resources lead to conflict and the idea that water is a commodity, which can cause water scarcity and an area where those who can afford water have access to it. Those that don't, can't. You have stronger and more unpredictable storm patterns, increased carbon emissions coming from drought soils, and the endangerment and extinction of populations and species. We've talked a lot about climate, but what is the difference between climate and weather? Climate is average, and it's typically about a 30-year norm. Climate is the average conditions in terms of temperature and precipitation that can be expected at a specific place at a specific time. Weather are atmospheric conditions at a very specific point in time. This is things such as having clear skies, cloudy skies, or weather such as snow or rain. One of the things that contributes to climate is circulation of heat in the atmosphere. Heat is moved in one of three ways: convection, conduction, or radiation. Radiation from the sun and from the Earth itself can transfer heat. You also have conduction of heat in areas where the atmosphere touches land or touches water. But most often you have that heat circulated through convection, where warm things rise and cool things fall. This convection is found in the atmosphere, in water currents, as well as in the mantle and the movement of plates. One of the ways convection is used to circulate heat in the climate is through what are called convective air cells. These are 3 specific areas on the Earth that have very specific weather and climate patterns associated with them. From the equator to the poles, those convective cells are called Hadley, Ferrel, and Polar. Hadley cells begin at the equator and move until about 30 degrees north and south. When 2 Hadley cells meet, they produce large amounts of rain and warm temperatures. Therefore, they are mostly found with 2 Hadley cells meeting at the equator in tropical rainforests. As Hadley cells move north, they lose much of their moisture but retain their heat. That is why at 30 degrees, where a Hadley cell and a Ferrel cell meet, most often you find deserts. Ferrel cells are found between 30 and 60 degrees latitude north and south. These are your temperate areas. Ferrel cells tend to be relatively wet and relatively warm, leading to areas of distinct seasons and very distinct ecosystems. When a Ferrel cell meets a polar cell, which is found between 60 and 90 degrees, you tend to start getting very cold temperatures with moderate precipitation. However, as you go into the center of a polar cell, you end up very cold and very dry. You also have this process called the Coriolis effect. That is caused by the Earth's rotation. Because the Earth is a sphere, one point is going to be moving faster than the other related to the equator and the pole. As this spin occurs, it causes wind patterns to bend. That bending happens clockwise in the northern hemisphere and counterclockwise in the southern hemisphere. This can impact the directions in which your wind patterns move and can also affect the way storm systems travel. Not only does convection work in the atmosphere, it also works in our oceans. The oceans work to transfer heat from the equator to the poles and carry cold water from the poles back to the equator to be warmed. There are 3 different kinds of circulation in the ocean. You have surface flow, deep flow, and then what is called the Great Ocean Conveyor Belt, which is found at the very bottom of the ocean. And this is called thermohaline circulation. The purple that you see on this diagram is the Great Ocean Conveyor Belt. It carries water around the entire Earth in about 1,000 years. However, it's important to notice a couple different deep and surface flow on this diagram. Take a look at the coast of North America. You'll see 2 different pieces, red and blue. Those make up the North Atlantic Current, which carry warm water up the coast of North America toward Europe. This current is incredibly important for maintaining climate stability in the northern hemisphere. It runs right past Greenland, which is a large ice sheet. If the freshwater ice from Greenland were to melt and make its way into one of those flows, it could change the salinity and the temperature, and almost completely stop that movement of warm air from the equator up to Europe. It could, in theory, lead to an ice age. And this is the premise of the apocalyptic movie, The Day After Tomorrow. So we've seen that our atmosphere and our oceans can work together to transfer heat from one part of the Earth to another. When we put these together, we talk about air masses. And the air masses can be defined by their temperature and their originating location. In terms of temperature, are they warm or are they cold? Warm are called tropical, and cold are called polar. We can also look at their area of origin. Are they coming over a body of water, or are they coming over land? Those who move over bodies of water are called maritime. Those that come over continents are called continent. You can have 4 different types: maritime tropical or maritime polar. You can have continental tropical or continental polar. These descriptors tell you about the water content, the humidity of the air mass, as well as its temperature. Maritime polar air masses tend to be very humid, but unfortunately very cold. Because they carry a lot of water and they're cold, these typically bring snowstorms. This is something you should be familiar with in terms of testing in APES as well as on the AP exam. Figuring out how these air masses work together to form weather patterns. While you won't be asked to identify these on the exam, it's important to understand how pressure systems work. Low pressure areas are where the air is rising. It tends to be warm. Low pressure rising air leads to condensation and stormy weather. High pressure systems are typically cooler and when the air is sinking. This leads to fair weather trends. You should also be aware of the existence of something called a front. A front is simply a moving air mass. We talk about them in terms of warm or cold. That is all you need to know about fronts. There are 3 specific types of major storm patterns you should be familiar with. One of those is the monsoon. This occurs in India and is an oscillation between summer and winter. In the summer, warm, heavy rains come in. In the winter, drier air leaves. That's it. You should also be familiar with tornadoes. Tornadoes are typically associated with thunderstorms and occur when 2 fast-moving swirls of air hit each other and begin to rotate. This rotation causes a funnel to form from the thundercloud. Very similar to the tornado is the hurricane. Hurricanes typically form over warm water, most often in the Atlantic, along the coast of Africa. As hurricanes move along warm water, they obtain more energy. However, as soon as a hurricane makes landfall, it begins to drastically lose its intensity. This is because it has lost the source of its energy. No more warm water. It's important to differentiate between a hurricane, a typhoon, and a cyclone. They all are basically the same pattern, but they differ in where they're found. Hurricanes are found in the Atlantic Ocean, typhoons are found in the Pacific, and cyclones are any of those patterns that are found in the southern hemisphere because they rotate in the opposite direction of northern hemisphere storm patterns. One of the major weather patterns to be familiar with is El Niño, or El Niño Southern Oscillation, sometimes abbreviated as ENSO. El Niño and its partner La Niña both are oscillating weather patterns in the Pacific Ocean. They occur between South America and Australia. However, they have weather effects in South America, North America, Australia, Indonesia, and continental Asia. They both affect water temperature, surface winds, fishing grounds, and major storm patterns across the globe. So how are these two patterns different? My suggestion for you is this. Learn the characteristics of one of the patterns because they are opposites of each other. If you know one, you can figure out the other. El Niño is a pattern that causes decreasing strength of surface winds. It also decreases thermocline, or the area of transition from warm to cold water in the oceans. Because the thermocline is less, there's less mixing between warm and cold water. This causes upwelling to decrease. Upwelling is when cold, nutrient-rich water rises up to the surface. But because that thermocline is flat and there's less mixing, upwelling doesn't occur. This loss of upwelling can lead to fish kill and a loss of fishing revenue for fishers in the area. However, the surface temperatures in El Niño in terms of water temperature increase. In the U.S., it's associated with warmer and wetter autumns. It also increases the chances of subtropical cyclones. However, in Australia and Asia, it leads to drought. La Niña is the exact opposite. Strengths of surface winds increase, your thermocline becomes more pronounced, which leads to more upwelling and more fishing. Surface temperatures drop, and it causes drier conditions across the U.S. and can lead to increased chances of wildfires and tornadoes. In Australia and Asia and Indonesia, it often leads to floods. This is a comparison of El Niño and La Niña to the normal condition, also known as the Walker pattern. As you notice, the big thing to see is the cloud diagram. In the normal condition, clouds and water temperature are moved from the coast of South America into Australia and Asia. In an El Niño pattern, that cloud cover gets caught between and stalls out. This means the ocean temperatures tend to be warmer there, but we're also leading to drought in Australia. The La Niña pattern pushes that cloud formation and that weather pattern further into Asia and Indonesia than it's used to. This is why you tend to have floods during a La Niña year. We've talked about geology. We've talked about the lithosphere. We've talked about the atmosphere. Now let's talk about the hydrosphere. Specifically, let's talk about our water resources. Globally, our water resources are broken into three categories: freshwater, brackish water, and saltwater. Saltwater has a very high salt content, and it's most often found in oceans. However, there are a few saltwater lakes found in the U.S. and in other countries. Brackish water is a mix of freshwater and saltwater. It tends to have a salt content that is slightly less than saltwater, but it is still pretty dense. Brackish water is found in estuaries, or areas where fresh and saltwater meet. Freshwater has a much lower salt content than ocean water. Note that freshwater does have salt in it, but it's at very low concentrations. Freshwater is the resource that we as humans are most concerned about because it is vital to our survival. So, where are our freshwater resources found? If you take a look here, you'll notice that 97% of the water on the surface of the earth is in our oceans. That leaves 3% of total water volume as freshwater. When we look specifically at that 3%, we find the overwhelming majority of it is locked up in ice caps and glaciers. We can't access it and we can't use it. About 30% is in groundwater in areas called aquifers. About 3% surface water, and there's 1% found other, most often associated with water being held in animals. Surface water is largely made up of lakes. However, it's also made up of swamps and rivers. One of the ways to look at our freshwater resources is to look at what is called a watershed. A watershed is a geographic area where all water runoff from a particular area empties into the same body of water. This can be a lake or a river. It is defined by boundaries that are often geographic, meaning mountain ranges, and they often lead from high elevation to low elevation. Watersheds are often made up of river systems. River systems have three major pieces: a headwater, a floodplain, and a mouth. The headwaters are almost always found at high elevations, and the original water source is often snowmelt. At the headwater, the water moves very swiftly, but is very shallow. As it moves from high elevation to low elevation, it begins to get wider and deeper. The wide and deep area of a river system is called the floodplain. This is called that because it often floods. That flooding brings nutrients that can make those areas very fertile for agriculture. And lots of human communities are built in floodplains. The problem is that when those rivers flood, those homes and property tend to be destroyed. Then you have the mouth of the river. This is where the river empties into another body of water. It may be an ocean or it may be a lake. At the mouth of the river, you may have silt deposits that build up and form what is called a delta. At the mouth of the river, depending on what the body of water is, you may form an estuary, where you will find brackish water and areas such as mangrove forests. Within the river system, you may also have smaller rivers or streams that join the larger river. Those smaller rivers are called tributaries, and the area at which they meet is called the confluence. Aquifers are where we find our groundwater. They come in two types, confined and unconfined. Confined aquifers are those that are found between two layers of rock. Unconfined aquifers are found in the soil above the bedrock. In order to access a confined aquifer, you have to use a very specific well called an artesian well. Unconfined aquifers are made up of what's called the zone of aeration, the zone of saturation, and the water table. The areas where the space in between soil particles is filled with water is called the zone of saturation. This is our groundwater. The area above that, where the soil is filled with air in the open spaces, is called the zone of aeration. The very top of the layer of zone of saturation is what we call the water table. When it rains, the water table rises because water infiltrates into the soil and builds up that zone of saturation. This is the process of aquifer recharge, when new water is added to the area. In order for an aquifer to be sustainable, the rate of recharge must be equal to or greater than the rate of use. So how do we as humans use our freshwater resources? Well, that depends on where you are. In high-income countries, the majority of freshwater is used for industrial purposes. In low-income countries, such as those that are developing, the vast majority is used for agriculture. Global trends show that the majority of freshwater resource is agricultural, then industrial, and domestic. Domestic water resource is the use of water for drinking, bathing, or cleaning. As we've seen, our freshwater resources are limited, and drastic changes in our global climate are making those water resources even harder to find. This graph demonstrates areas where freshwater is becoming very scarce. The darker the color, the more conflict there is over freshwater resources. This can be over water rights to a stream or an aquifer, or simple loss of a freshwater resource, and now people are competing for that. It's highly likely that in future years, unless we become more sustainable in our freshwater use, more armed conflicts will break out over water resources. It is important to note that freshwater resource conflict is largely based on location. It's more likely to happen in middle or lower developed countries and areas with unstable governments and infrastructure. However, it can occur in developed countries, especially when areas are undergoing drought and industrial companies are using much more water than their allotted amount. Can we manage these conflicts? It's possible, but there are a large number of considerations to keep track of in order to make these plans. Should water be privately owned and sold as a commodity? Should water be made a public utility that is regulated by the government? Or should people have access to a lottery? And the closer you are to the front of the line, the more likely you are to get your freshwater resource. There is really no correct answer for this. Every location and every country has to make its own decisions about how they manage their freshwater resources to avoid conflict between groups.